Hello again. This is the quick complement I was just talking about uh, at the end of our lecture. Okay, we're talking about the atomic packing factor here. The APF is the volume of the number of atoms in a unit cell divided by the volume of a unit cell. The cube here is a unit cell. The number of atoms are those atoms you saw on that picture I showed you earlier, which I'm going to show again. And okay, let's calculate the APF here. So we have a cube, and you remember the name of that A dimension is called the lattice parameter. Lattice parameter is A, the size of the cube. From that, we saw that from this corner to this corner here, it's A root 3, right? So how many atoms did we say we had in this box for BCC? We had 2 atoms. For BCC, right? What kind of a geometric shape is an atom? It's a sphere, right? So we were precisely at the point where we were calculating that numerator here, the volume of the number of atoms in a unit cell, right? So now, what is the volume of atoms in a unit cell? We've got the numerator then, APF, and we know we have 2 atoms in our BCC structure, and we know that the volume of each sphere, each atom, is 4/3 by r cubed, right? So we've got the numerator here. So now the denominator. The denominator, we see that we have a cube. So the denominator is the volume of a cube, volume of a unit cell. Remember, this cube is called the unit cell. It's a cube, right? Yeah, so I'd love to solve this issue, but I've got a little problem here. I've got a radius here, and I've got a lattice parameter here. So how do I relate that? But those X-rays help me see inside the atom. So now, along the blue diagonal, body-centered, that blue diagonal here, okay, that length of root 3a, I'm writing it root 3a, a root 3, okay. Well, let's open again I'm going to share that. All right, it's the one here. Okay, click it up. Okay, along the blue diagonal body centered, that length of a root 3 well, I want you to see a root 3 here. This is the A root 3. I want you to see that they are, and it goes through the center here, so if you can visualize that. So they are 4 radiuses along that line. You see you have 1 radius here, you got 2 radiuses here, which is a diameter, 2 radiuses, and you've got another radius here, and the line goes from here to here through the center. And remember, and maybe you would have asked me if we were live here, but they touch each other. Those atoms are actually touching each other. So you've got basically, that's how you can relate A to R, because in this distance of A root 3, you've got all those atoms touching each other. You've got that radius plus 2 radiuses plus 1 radius here. So that's a fundamental relationship for the body center, which is actually, it's in a different color. A root 3 is 4R, all right? A root 3 is 4R, 4 radiuses. That you relate the lattice parameter A with the radius of the atom here. Okay, so now we can proceed to solve. I'm switching back to the whiteboard. Okay, we can proceed to solve. And remember, we found on here, we found A root 3 equal 4R, 4 radiuses of atom. So you see the numerator here as R cubed. All right. So we are going to solve for R. It's A root 3 divided by 4, right? So what's R cubed going to be here? R cubed from that, the calculation of our APF here, you see? We are trying to calculate that APF. So what is R cubed going to be? R cubed is going to be 3 root 3 A cubed divided by 4 cubed over 4 cubed, which is 64, right? So this is R cubed. So far, so good, I hope. So substituting this, and take good notes because this will help you during the first lab. You're going to be replicating a lot of this, okay? So we have R cubed. So if you plug back into that R cubed into here, okay, you will, okay, I'm going to write the formula again. You're going to have times 2 times 4 third pi third pi divided by 3 root 3 A cubed divided by, and that's over 64 A cubed. Well, that's kind of convenient because now it doesn't matter whatever metal you have as long as it's at its body center cubic. So you see the lattice parameters will cancel, A will cancel. Okay. That in turn give you what? The 3 will, okay. The 3 will, the 3's will cancel here. Okay. You can simplify the algebra this way, and we'll have 2 times 4 is 8, root 3. Okay, so we make 8 root 3 pi divided by 64. Okay. Okay, all right. So 864. Okay. 8 times. Okay. So it will eventually give you root 3 pi divided by 8. So if you take your calculator now and simple calculation, well, what will you find? You will find a number with 2 significant figures here. That's what we want, which is the atomic packing factor for all body-centered metals, okay? And this number is 0.68 or 68%. Well, that is an important result. That's the way nature made it. Yeah, that's the way nature made it. So let's look now at the FCC slide that I showed earlier. So FCC, here is the FCC. So for the FCC, we had 4 atoms. Okay, that's what we found earlier. But now, as the name indicates, these atoms are touching, not on the body diagonal, but on the face diagonal. You will see they are touching on the face diagonal. You see the face diagonal here? That's a face diagonal. All those atoms are touching, but not on the body diagonal, which was not on this one. It's touching on the face diagonal. This is called the face diagonal, right there in red. So if this is A here, and this is A, well, the face diagonal is A root 2, A root 2. And in all body-centered cubic, it's A root 2, A root 2. Okay, still using Pythagoras. So in all metals, it's always like that, whether it's copper or silver or aluminum or gold, it does not matter. They're all going to follow this structure. X-rays tell us that, X-rays. This means, folks, that on the face diagonal, A root 2 is always going to be 4 radiuses. It's even more a bit difficult to visualize here, but it's for 1 radius. Oh yeah, here you see 1 radius, 2 radiuses, 1 radius. So 4 radiuses. Okay, sorry for this interruption. Any questions on anything so far? If you have any question, let me know, send me an email. But so in the real world, okay. So in the real world, those spheres will all be touching. They will be actually touching. It's not a figure of speech or imagination. They are touching. So what's actually really interesting about this is that you'll see you'll see that in one of the lab exercise. Well, if I ask you, if I gave you some unknown metal and I said, find the density of this, what would you do? Well, let's say it comes out to be 2.7 grams per cubic centimeter. You look in a book and say, hey, that looks like aluminum, 2.7 grams per cubic centimeter. But here the cool thing that X-rays tell you the same thing. So when you look here, you could actually see on that small scale and calculate the very same density. This is really the beauty of it. This is a scientific breakthrough and a crystallography that is, reconciles our atomic view with the microscopic view. So that relationship So sorry for that. Because it's kind of a cool thing to be able to see the connection with these atomic arrangements that you already kind of had exposed to in strengths of material. And that's why I'm going through that. The atomic factor is a bit like density again. And but I would say it's like, it tells you how nature has preordained the way the stuff comes together in one class versus another. And again, I was talking earlier about packing for a trip, and you put the stuff together in a suitcase. Some people do that really good. Some people fold and things, and others just throw their stuff in the suitcase, zip the suitcase, and it's coming apart at the seams. Well, sort of thing. Think about that analogy to nature. Something fit together more efficiently than others, and there is a reason for that. So the BCC factor for the BCC atomic packing factor was 68% for the BCC. What would it be for the FCC? Well, so how do we determine the APF? The diagonal here is A root 2. Remember, the APF, atomic packing factor, is the volume of the number of atoms in unit cell divided by the volume of a unit cell. All right, so we had 4 atoms for BCC, FCC, sorry, 4 atoms for FCC. So what is the numerator? It's going to be 4 multiplied by the volume of each atom, each sphere, 4/3 pi r cubed. That's our numerator. Now the denominator is the volume of a unit cell, the cube. So it's the same. It's always a cube. It's A per A per A third. All right. So well, again, we have the same 2 variables A and R here that we need to substitute to link. But our substitution now is, as we just saw, is A root 2 is for R, right? So if you cube that, you got R, I'm sorry, first, R is A root 2 over 4. So if we cube this, R cube is A cube multiplied by 2 root 2 over 64. All right, so we cancel the 2's or 3. All right, we are going to substitute that here. Okay. So it's 4 multiplied by 4/3 pi A cube 2 root 2 over 2 root 2, 64. Yeah. 64. Okay. And so eventually we'll we have so this, okay, all right. Over A cube. So the A cubes cancel out. Okay, so eventually you're going to have 16 pi A cube have already cancelled, etc. Right, by so our A cube, I'm going to write it again because it was not clear the first time. Okay, over 32 A cube. Okay, so we're changing color to make it a bit more clear, hopefully. Okay, so that's what we did earlier, but A3 cancel out. I got 16 here, 32 it makes 2. Eventually you find pi root 2 divided by 6. And what does it do? What did it give us? Well, 0.74 or 74%. All right. Okay. So again, in the other class FCC, well, that we just talked about, um, right now, the face center cubics, the aluminum, the copper, the nickel, so forth, they are all face centered, which means that we have, again, four radiuses we saw, and they're all touching. So that is to be remembered, they all touching. So it's easy. All right. Um, so again, I go back on that, but the BCC atomic packing factor was 0.68, and the FCC here is 74%. So we see clearly, having 74% packing factor, that which one of the material is more efficient in terms of packing. The face center, of course, is higher as opposed to the other one, which is 0.68 or 68%, which was for the BCC, right? The FCC 74%. But now remember what we were talking about recently about ferrous metals. What is the weakness of ferrous metals? What is their vulnerability? Oxidation and corrosion. Okay, that's the vulnerability. Think about what I just told you. Um, it's the body-centered cubic of which iron is part of as ferrous metal is 68%, right? Copper, aluminum, stainless steel, gold, silver. You remember what class they are? FCC, right? That's quite interesting. Wow. So think about it. The guy that is a little bit more efficient with packing stuff, in some way, it's like a built-in resistance, for other stuff to get in. So remember that we have FCC, which has a higher packing factor, and it corresponds to those metals like copper, aluminum, stainless steel, gold, etc., which are corrosion resistant. And it's more because it's more packed. It's more difficult again uh, for other stuff to get in. So it's built-in resistance. So keep that image in your mind, and it's actually it's more than an image. It's what it is. So this introductory exercise has been that instruction of understanding how things at the atomic level can inform us of the greater macroscopic properties, be corrosion resistant or strengths of the material itself, which we'll be seeing in our subsequent labs. Um, what we just saw are two out of the three folks. Two out of three. The third is the hexagonal close pack. The geometry, and I would say the trigonometry of that warrants a little bit more time. And this is addressed in the third asynchronous lecture that I published on Sunday yesterday, which was prepared by Professor Vlodkovsky. This will also be part of a lab next week. So this week. So I strongly encourage you to watch that asynchronous lecture provided yesterday, which is continuing, a continuation of what we were talking about. Again, we discussed two structures, FCC, BCC, and the third one is the one in the asynchronous lecture, which is HCP. Okay, that's it for now, and thank you again for your attention.